Now that you've had an opportunity to learn a little bit more about how to predict a double replacement reaction, whether it should occur or not, based on if a precipitate will form, we're now going to use those solubility rules to determine the states of all products that are provided to us in these first equations. And then if a reaction should occur, so if a solid, liquid, or a gas will form as a precipitate, then we're going to go ahead and write out the net ionic equation as our final answer. So let's go ahead and do a couple of example problems. In this particular video, I'm going to work through problems 1, 4, and 9 on this worksheet, and then the rest of them you can work on your own and just double check your answers with the answer key that's been already posted. All right, so taking a look at this, we have silver nitrate mixing with potassium chloride, and we get two products, so silver chloride and potassium nitrate. Looking at the solubility rules, silver is kind of special and it has its own rules. One of the things we'll notice is that silver chloride is an insoluble compound, meaning that it is more attracted, the silver and chloride ions are more attracted to each other than they are to the polar ends of the water molecule. So it will precipitate out in this reaction and form a solid. So we are going to go ahead and label that as a solid. And then potassium nitrate being our second product, the kind of cool thing is all nitrate compounds are soluble, which means that they dissolve in water. Nitrate's more attracted to the positive region of water, so that hydrogen ion part of water, than it is to the cation that it came in with. So all of these are going to be soluble. All nitrate compounds will have an aqueous label. Now, if we had had two aqueous labels there, then this reaction would not occur. There would be no observable change in the well plate or whatever reaction vessel that we're studying. And so we would just say no reaction and we would move on. But because this one does occur, the next thing we're going to go ahead and do is we're going to double check to make sure that that equation is balanced. So take a minute and look through that if you need to pause the video and just double check to make sure that that equation is balanced. Okay, so one thing you should have noticed is that it was. A lot of times when we write these out when they're balanced, it's kind of nice. The next thing that we have to do is we need to write down the net ionic equation. Now there is a version of this where we could actually take and break down, and I'll just kind of do it quickly here, where we could go ahead and break down each one of the ionic compounds into their ions. And then at the end, we would cross off everything that's the same but on opposite sides. That tends to take a little bit more time, so I'm going to go ahead and just show you what we can do from the molecular equation to make that net ionic equation writing easier. So if I look at my solid is untouchable. I can't break that apart. It's not going to be floating around as individual silver and chloride ions in solution once the reaction has occurred. So I can't do anything with that. But what I can do is I can look at the aqueous solutions and find anything that's the same but on opposite sides of the equation, and I can cancel those out. So I can't cancel out silver because silver is part of my solid. But nitrate is fair game because it's aqueous on both sides. So it would be floating around as NO3 with a 1- charge, both as a reactant and as a product. And then I can take a look at my potassium, and it's the same thing. So because they're both aqueous on both sides of the equation and aren't involved in the actual making of the solid, I can go ahead and cross those off as well. And then the other thing that I can do is look at chlorine, and because chlorine is part of the solid, now I know what species I need to use in order to write the net ionic equation. So let me just show you how to do that. Because this is aqueous, because the silver is an aqueous solution, we have to write it with its charge. So we're going to, again, go ahead and write Ag positive with an aqueous symbol. And then we come over here to this chlorine, and again, because the chlorine is aqueous, we have to write it with the charge that it would have. If it dissociated from the potassium, we have Cl with a minus, and that would also be aqueous. And that's all we have on the reactant side. So now we are going to put the arrow to indicate that a reaction is occurring, and then we write down the solid. AgCl solid. And that's the net ionic equation. And it is balanced. We have one silver ion and silver in solid form, and then one chloride ion and one chloride in solid form. And that's all we have to do. All right, so let's take a look at our next problem, which I said would be number 4. Number 4 requires a little bit more effort from us because now we actually have to write out the actual compounds before we can do anything else. So let's go ahead and do that. This is what I love about chemistry at this point. There's a lot of knowledge that kind of has come to this, that you have acquired that has allowed you to understand why these things are working. So manganese 2 is Mn with a 2 positive. And that's going to go with chloride, so Cl with a 1 minus. Writing that as a compound, again, just as a reminder, I think it's a good time to review. This is kind of what we're looking at, right? We never write the charges, and if it's a 1, we don't write it. So that's MnCl2. Again, because this is a solution, we'll write down aqueous. We're going to add that to ammonium carbonate. Now, ammonium is NH4 with a 1 positive charge, and carbonate is CO3 with a 2 minus charge. Again, if I'm writing this out, the 2 is going to jet down there. The positive would have come down here, right? It's a 1. Erase the charges. Put brackets around anything that already had subscripts. So these polyatomics have to be protected. And then this is actually going to be our new formula. So go ahead and take that one down to here. All right, now we're at the point where we're doing our arrow. So go ahead and put that in. And now we have manganese 2 carbonate. So that's kind of nice because it's Mn with a 2 positive charge and CO3 with a 2 minus charge. And we know that that's going to be MnCO3. So I'm going to go ahead and finalize that and scooch that over. I just realized I didn't put the aqueous, so I'm going to go ahead and go back and do that. So putting the aqueous here and then moving on. I'm going to come back and determine the state of that here in just a minute. And the last one I have is ammonium chloride. So again, kind of a nice little compound because you have NH4 and that had a positive charge, and then chloride had the minus, so those charges cancel out and we don't have to do anything else with that. So looking at my solubility rules and looking at the rules for carbonate, MnCO3 is going to be a solid. It's insoluble in water, so it will precipitate out. Ammonium chloride, on the other hand, will be soluble, so it will remain dissolved in water. All compounds involving ammonium will actually be soluble, so that's kind of a nice little rule as well. So this will remain aqueous. Now, next step is to balance out the equation. I have 2 ammoniums here, only one on this side. So I'll go ahead and put a 2 in front of that. And then looking at my chlorides, I have 2 on this side and 2 on that side, and then everything else checks out. So now what I want to do is the same kind of little thing I did before. I want to write the net ionic equation since this reaction will occur. Here's the other way I can do it. So in the first part of the video, I showed you a trick, and I'm going to show you the reverse trick. So instead of going through and canceling out all of the things that are the same but on opposite sides, what I can just do is focus my energy on the solid. So what I'll do is I'll write down the solid as the product first. So MnCO3 solid. And then I'm going to break this compound down. So I know that I had Mn 2 positive and CO3 2 minus in order to build that compound. Anytime you have an ion, those are aqueous. And so now all I'm going to do is move those over to the appropriate side. They should be reactants, so I'm going to slide them over to the actual reactant side. I'm going to do that by giving myself some more room. And then I'm going to just put a plus symbol in between. And that's all I need to do. So there's a couple of different ways you can do this. One way is to, again, understand what the solid is and then go through and cross off anything that's the same on both sides. So I have 2 NH4s on this side that are aqueous and 2 NH4s on that side that were aqueous. And then I had 2 chlorines on this side and I had 2 chlorines on that side that were both aqueous. And what I was left with was Mn and CO3, both aqueous. Well, that's where I got this from. And I got each of these just by breaking down the solid into the ions that had formed them in the beginning. So there's a lot of different approaches, a lot of different methods that can be used. Whatever method kind of makes more sense to you, that's the one I would encourage you to do. And again, if neither one of those is working for you, the other option is to break everything down into the ions. And you can do that for everything that's not a solid, and then cancel out everything that's the same on opposite sides of the equation. And then write your net ionic equation. It just takes a little bit longer. All right, last example is example 9. So in the second half of the assignment, what you're being asked to do is to predict the product. So the first half of the assignment, it gives you what the product should be. Second half of the assignment is going to allow you to practice that skill a little bit more. So let's again go ahead and take a look at what we have for compounds. So cobalt 3, that's a calcium. So cobalt 3 positive is going to combine with bromide, which is Br 1 minus. And then potassium is K 1 positive, and sulfide is S 2 minus. Now, the only reason why I didn't write the compounds there is I want to be able to use those here in just a minute. So I'm going to go ahead and write out cobalt 3 bromide, so COBr3. And because this is a precipitation reaction, I know that those are going to be aqueous. I could also use the solubility rules to double check that. But if they're on the reactant side of a potentially double replacement reaction, you don't really have to double check those. Potassium sulfide then would be K2S, also aqueous. Now it's my job to write out the products, and that's why I didn't want to kind of combine those ions, because I want to show you how simple this actually is. So what I'm going to go ahead and do is, I know that a double replacement reaction is just a switch, right? So cobalt was with bromine and it was attracted to that negative charge. So cobalt is going to find the next negative charge. So that's the sulfur or sulfide. So I'm going to go ahead and bring down my cobalt and my sulfide. One of the reasons I love notability. And then the only other 2 that are left over is potassium and bromide. And again, the rule is potassium, because it's the cation, goes first, and then bromide, because it's the anion, is listed second. And then from there, I'm going to go ahead and write out what my actual compounds are. So cobalt and sulfur should form a CO2S3, and then this K and Br, the charges just cancel out because they're one positive, one negative. So I'm going to slide this over here just a little bit. That's the first step. So in the beginning part of the assignment, everything was laid out for you, all the compounds. You just had to use solubility rules to determine if it was solid or aqueous. In the second part of the assignment, you had to write everything out, but still all the compounds were given to you. And in this third part of the assignment, you're actually predicting what the products are, and then looking at solubility rules, and then figuring out whether or not the reaction occurs, and then writing your net ionic equation. So looking at the solubility rules, I'm actually going to look at potassium bromide. Looking at potassium bromide, potassium is one of those elements, alkali metals, that will always form soluble compounds. So no matter what the anion is, the potassium will cause this thing to be soluble in water. So this is going to be my aqueous. And then my sulfide, especially with the cobalt, this is going to be my solid. So this reaction will occur. And again, the next step is to make sure that the equation is balanced. So go ahead and throw in the numbers for that. So just kind of doing some quick looking at this. I was looking at my bromine and there was 3 there. And then I was looking at potassium and there's 2 there. Because those things come together in KBr, I needed to find something that they had in common. So that's going to be a 6. And because that's going to be a 6, I'll put a 3 in front of the K2S. And then with my bromine, I'll have to put a 2 in front of the COBr3. And actually what's really nice is that works then because cobalt has 2 and the sulfide has 3. So everything's balanced now. Don't forget that step. It's so easy to kind of just get rolling with this and then you forget that step and then you mess up. Okay, again, I'm going to use my quick, I like to call it my shortcut or cheat. So I'm going to go ahead and write down the solid CO2S3, and that's going to be my solid. And then where did that come from? Well, it came from the fact that I had cobalt, and cobalt had a 3 positive, but because I have a subscript of 2, I know I need 2 of those. And again, anything that has a charge is aqueous. Let's flip it over a little bit. And then my sulfide was S2 minus, and I have 3 of those. So I'll need to make sure I put a 3 in there. Again, because it's an ion, I need to make sure it's aqueous. So as long as the numbers of ions match up with the numbers on the product side, then the cheat makes a lot of sense and it actually saves you a tremendous amount of time versus having to break down every single thing into its ions and then cancel things out and then write over the equation over again. All right, hopefully that helps you. There's a total of 10 problems on this homework assignment. Not all of them are reactions. So the nice thing is if you find the ones that aren't, you just write no reaction and you don't have to write anything else beyond that. If you have questions, feel free to, ask during your time that you're physically present in class. I will definitely come over and work with you to make this a little bit easier. Again, you can work through it, check the answer key. If you find that you're able to do that just fine, awesome. If you find that you're making a lot of mistakes and you want some additional help, again, reach